Hello, everyone. My name is Stojan. I'm a software engineer at Axel Springer, and today we're going to talk about error handling beyond the standard library. Let's go over the agenda for this talk. First, I'm going to describe the problem, the app that we're going to build. Then we're going to see how we can handle the happy path. Then we're going to talk about error handling strategies in Kotlin and other languages. Then we're going to go back to building the app with error handling. And to do that, first we're going to split the problem into two sub-problems, accumulating errors and failing fast. And we're doing that because both problems have different requirements. By the end of this talk, hopefully you'll be familiar with what's there in terms of error handling in the Kotlin standard library and what's there in the error library and how it can help you build better apps. So we're going to build an app that needs a sign-up form. And to sign up for our service, users will need to provide some data. They need to provide their name, and they need to provide either their email or a phone number. OK, I guess I use the keyboard because this is how the app should look like. We have a screen with two fields, one for the name and the other for either the email or a phone number. We also have a button to switch between either email or phone number. We also have a submit button that, when clicked, executes a network call and validates the form. The flow for the happy path looks like this. We have a displayed form. The user clicks submit. We call the API. So this is the happy path, ignoring error validations. The API replies. We store some token that we get from the API, and we end the flow. Sorry. Sorry about this. OK. I guess I somehow lost the slide, but let's talk about things that could go wrong outside the happy path. So we could have an empty form. We could have a user that entered some invalid data. The network could be down, so the network call can fail. We could have made an error while coding and configured retrofit or whatever library we use there wrongly. That can also throw an exception. And we could go out of memory if the request is too large or the response is too large and we're not using a library that supports streaming. And probably a lot of other things can go wrong. OK, let's code the app now on the happy path. We need a sign-up body that will contain the name and either the email or the phone number. Note that name is required, so it's not nullable, and email and phone number are nullable. But one of them is required for this to work. And we have a sign-up result for whatever the response from the backend is. And then we're using retrofit to execute the API call. Here we're using the suspend support, where we have a suspend function. We have the sign-up body with the add body annotation. And as a result, we have the sign-up result. And here I'm using Kotlin X serialization, but we could use any other library, and this would not change much. In the presentation layer, we have an enum class for the ID type that we're going to use currently. This can be an email or a phone. We have a form field class that will wrap whatever value is in the form, and an optional error message that's related to that field. And we have a view state class that has a show progress to control progress bar, has an optional error screen for some sort of generic error, like network is down, the ID type we are currently displaying, and the two form fields we saw in the UI. And we can use Compose to render this model, or we can also use the Android view system to render this model. And then in our view model, we have the sign-up class that's created by retrofit that's going to be injected. We expose a mutable state flow with our state. And when the user clicks the submit button, we call the onSubmit function that takes that information, creates the body, updates to show loading state, and then we launch a coroutine, and we call our sign-up method, and we store the token. And this is our happy path ignoring errors. And I found my slide that I lost. So I've already explained the things that can go wrong. Oh, I forgot the JSON one. This is a fun one, if suddenly we decide to switch our API to XML. Now that we know that there are a lot of things that can go wrong, we can create some additional requirements. So before we send the data to the backend, we want to validate it just to make sure that things are there and they're probably correct. The backend will also do additional validations, stuff that we cannot do on the client, like checking a user with that email doesn't already exist. And then when users will make mistakes, we also want to help them fix them. So if there is an error, we want to show it as close as possible to the source. So this is how the UI would look in case there are errors. In the middle, we can see errors from the local validation or coming from the backend validation in the API response. In the screenshot on the right, we can see a generic error, for example, if the internet is down or the backend is down. So what does it mean for a function to fail? It means that there is an input for which it cannot compute an output value. For example, the toInt function from the standard library takes a string and returns an integer. If the string we've passed in is not a valid number, it has to fail somehow. In this case, the toInt function throws an exception if we pass an invalid input. Functions can also fail because of an external reason. For example, when we call the signup function backed by retrofit, if the server is down, it will fail. And that's something not related to the input, but related to an external reason. Strategies for dealing with failure in Kotlin. Roman Elizarov wrote a really nice blog post called Kotlin Exceptions. And there he describes a few strategies to deal with them. Today I'm going to go over some of them and some that are not in the blog post. And we will see how we can use them to solve our problem of validating and submitting a form. So, options for dealing with functions that can fail. The function can return some sort of sentinel value to indicate the failure. We can use checked or unchecked exceptions. We can return nullable types. We can return a sealed class hierarchy indicating a success or failure. Or we can move the validation problem to a different place. Sentinel values were popular in the C language. It didn't have exceptions, so people had no other choice but to return sentinel values. For example, here, fopen function can fail if the file doesn't exist, for example. And developers have to remember and check for this special value, in this case, null. And only if it's not null, they can do their logic. Note that unlike Kotlin, C doesn't have null safety, so the compiler here doesn't help you a lot. And this is tedious, easy to forget, and hard to debug. So Java came to the rescue and introduced checked exceptions. So now file input stream can throw an exception in case the file is not there. And the compiler will force you to handle that exception by either handling it or rethrowing it, whatever. And this is an improvement over Sentinel values, but exceptions, checked exceptions, have their own problems. And some of those are exceptions that never happen can be declared as checked. APIs with long exception lists. Developers will catch and ignore exceptions. Checked exceptions don't work well with higher order functions. This was exposed with Java 8. And fatal versus expected can depend on the client calling a function, not on the type of the exception in certain scenarios. Kotlin doesn't have checked exceptions, and exceptions in Kotlin are typically used for logic errors. For example, the update order quantity function takes a quantity and an order ID, and quantity must be positive. So here we use the require function to assert that quantity is greater than 0 and throw a legal argument exception if it's not. A quote from the article I mentioned before, use exceptions for logic errors, type safe results for everything else. Don't use exceptions as a workaround to sneak a result value out of a function. This is a quote by Roman Elizarov from the article. So Kotlin brings us another option. We can use nullable values to signal failure. For example, and the standard library has a lot of examples for this. The toInt function that returns an int, takes a string and returns an int, will fail with an exception in case of an invalid value. There is also, this is useful when you have some constant in the code and you want to convert it to an int. There, an invalid string would mean a logic error or something that we've written in the code. This function also has a dual. It has the toInt or null that takes a string and returns a nullable int. And in case of an invalid input, we get a null back. And this works well for dynamic values like user input, and the compiler will force us to deal with the possibility of it failing. So in Kotlin, we can use nullable values, and the compiler will force us to deal with the failure, just like checked exceptions in Java. However, we are limited to a single failure reason, and we cannot provide any additional failure information. In cases where we could have more than one failure reason, or we need some additional failure data, we can use a sealed class. For example, when we have a string and we try to parse it in a date, and this operation can fail. In Java, the typical way would be to throw an exception. In Kotlin, we can create a sealed class, parse date, that has a success subtype that contains the date, or a failure subtype that contains some additional information about the failure. And we can use that, and callers of the function will be able to use the when expression and check if it's successful or failure, and react accordingly. These two approaches, returning a nullable type and a sealed class, modify the output of the function to indicate failure. This works for different type of failures, and we have additional data. Another strategy is to move the problem someplace else. If we have an email and we are modeling it as a string, Here, both the sign up and the reset password functions have this require clause, and we're treating the invalid email as a logic bug here. The check is duplicated. We can fix that by extracting it into a function. And this is not the place where we can handle the failure. If this email is coming from user input, we want to handle it close to there, not here. So this is just like a backup that if somehow we forget to validate the email, here we're just making sure it's valid. To avoid this duplicate check and this require, we can avoid this require by moving the problem somewhere else. To do that, we can create a value class email that has a private constructor. We can create a create function, factory function, that takes an email and validates it. If the email contains the @ sign, we create an email value, otherwise we return null to signal the failure. Now, sign up and reset password don't need to have that require as first line and make sure that the email is valid, because the only way to create an email object is to use the create factory function, which validates the email. So we've moved the problem to a different place. Now that we went over the techniques for handling failures, let's go back to building our sign-up form. I'm going to introduce a few domain types. Sign-up ID will be a sealed interface that can be an email or a phone number. We're going to add some validations later. And then sign-up data contains the name and sign-up ID. This enforces that one of email or phone number exists in the sign-up data. So when we pass it to the other layers of the app, there is no possibility to fail because information is missing. And here, email and phone number get a value class like a separate type, and name doesn't, because I've made that choice. Because for me, email and phone number have more interesting validations. Name doesn't really have an interesting validation. Then I also have an inline class for the token that the backend returns. I will also create a user repository that does the sign-up by calling the retrofit. And here I'm working with the domain tabs. This inverts the dependencies between the data layer and the domain layer. It makes the data layer depend on the domain layer. So the flow, when we add error handling, should look something like this. We have a form. When the user clicks the submit button, we do a validation of the form. If that fails, we show an error. If the validation succeeds, we need to call the API. The API call can also fail. If that fails, we need to update the UI. If the API call succeeds, we store the token and we go to the next screen. We have two steps that can fail in this scenario: the form validation and the API call. And the requirement here is to abort on the first error. If we zoom in to the form validation part, we will see that when we validate the form, we need to validate the name and validate the email or the phone number independently of each other. When we validate those two things, we need to put them together. If both of them fail, we need to group the errors together and return all of them. Only if both of them succeed, we want to continue with the flow. So here we validate the data independently, and we want to accumulate the errors, so there is no failing fast here. The validation rules that I'm going to use are: the name can't be blank, the email must contain the @ sign, the phone number has to start with a plus, and it has to be 4 characters long, at least. These are my arbitrary rules for this app. In your projects, you probably have different rules, maybe more complex validations. So let's talk about the validation problem first and how we can accumulate errors. If we use the strategy of returning nullable types in case of error, we can implement the validate name function that takes the name as a string and returns a nullable string, which is null in case of an error. Here, if the name is blank. We can also implement a validate email function that takes a string and returns a nullable email. However, validate phone number that takes a string and returns a phone number, and validate form that takes a name, ID, and ID type and returns sign-up data, we cannot implement. The reason for that is phone number has two different reasons to fail. One of them can be true, or both of them can be true. Sign-up data also has like a lot of different combinations for which it can fail. We want to return all the error messages together so that the users can fix them in one go. So nullable types work well for a single error reason, like the email or name. They don't work for multiple error reasons. So for validating a form, we cannot use nullable types. Let's try to use a sealed class as a result type. We can create a phone result for validating our phone number that has a success value and the valid phone number inside, and 3 objects for the error cases. This can also be modeled in a different way, but let's take this as an example. Then our validate phone function can take a string and return the phone result. This function we can implement. We can create a similar result type for our form, where we have a success subclass that has the sign-up data inside, and an error subclass with a list of field errors. Then we can create a validate phone form function. This takes the name and the phone number. It delegates to the validate name and validate phone functions that return nullable types to validate the validate name that returns a nullable type and validate phone that returns a sealed class to validate the name and phone number respectively. And then we can do a when check that is successful if the valid name is not null and the valid phone is a success. And then we can construct our form result from there. We also need to handle all the possible failures where one or both of these validations fail. And then we also need to add this illegal state exception, which never happens, but we want to make the compiler happy. We would do a similar function for email validation. Now we have support for multiple and different errors. We have the compiler helping us with smart casts when we check is not null or is success. We have to add that else branch to make the compiler happy. It's not great, but it doesn't scale well with the parameter count. So for two parameters, we need to handle 4 cases. If we add another parameter, then we have 8 cases that we need to handle. Let's see what's there in Arrow that can help us. Arrow is a family of libraries. It has like 4 main ones: core, FX, optics, and analysis. In this talk, I will only cover parts of Arrow core. For error accumulation, Arrow offers the validated type, which is a sealed class with 2 subtypes. It has a valid subtype or invalid subtype. And we can modify the signature of our validate phone function to take a string and return a validated. In case of failure, we have a string, and in case of success, we have a phone number. We can do our validation, and if the thing is valid, we use the valid extension function to create a valid instance with the phone number inside it. In case it's invalid, we can use .invalid to create an invalid instance. Note that this still has only 1 error, support for 1 error. If we call the validate phone with an invalid data, we get an invalid instance with the error message. If we call the validate phone with the valid phone number, or something that looks like a valid phone number, we get a valid instance with the phone number inside it. So let's talk about how we can accumulate errors now. To accumulate errors, Arrow offers the non-empty list type. This is a list, just like a normal list, but it has the constraint that it needs at least one element. That means, unlike the Kotlin standard library list, where you have a first element function that throws if the list is empty, this one can have a head function that returns the first element from the list, but never fails. Another common name for the non-empty list is null. We can create an instance using the non-empty list of factory function that requires at least one element. Or if we already have a list, we can use null.fromList, pass it the list, but then it returns an option, meaning that if the list is empty, it will return none, and we have to handle the possibility of this failing. So non-empty list is typically used on the left side of validated, and this is a very common scenario. So Arrow offers the validated null type alias, which is a validated that has a non-empty list on the left side and some success type on the right. That means that we can update our function to validate the start of the phone number, to take a string and return a validated null with either a string on the left or a string on the right. We can use our normal check for the start and create either a valid instance in case of success or invalid null in case it fails. Our second check for the phone number is validating the length. And we do the same thing here. We check for the length. If it works, we create a valid instance, or we create an invalid instance with our error message. So now let's put these two things together. We can create a create function that returns a list of strings in case of failure, or the phone number. For the start, we delegate to our validate start function. And for the length, we delegate to our validate length function. So if we are doing this manually, we have that when check with all four cases. If we do it with Arrow, we have a zip function that takes the first validated and the second validated and takes a lambda. The lambda will only be executed if both of these things are valid. That means that the lambda inside has access to the valid values. Here, both functions get the same phone number as a valid value. So I'm ignoring one parameter, and then I'm creating my phone number instance. This zip function has overloads with up to 9 parameters. So for any number of parameters up to 8, we don't get any additional boilerplate. And in case of failure, it will merge all the failure messages. And the way it does that is the first function returns a list of strings in case of failure. The second function does the same. So it will create a third list that has the elements from both lists. It will put both lists together. So if we call now phone number.create, we get 2 error messages if we call it with an invalid phone number. If we call it with a valid, again, we get the valid phone number. So to use this in our problem, we need to introduce some domain models for our errors. Form field name for which field has a problem. Form field error is the name and a list of problems that it might have. And then for the result of form validation, we can have a validated null with a list of form field errors or our success type. So I'm going to use the nullable strategy to validate the name. For my email, I'm going to also use the nullable strategy and create the inline class and put the create function in the companion object. Phone number also gets a value class with a private constructor and a create factory function. It delegates the validation for the start and length to the validate start and validate length functions that we already saw, and then uses zip to create the phone number if both validations work. And validated has interop with Kotlin's nullable types. So I have the validate name function that returns null if it fails. I can convert that to validated using validated from nullable, so that I can merge that together with my phone number.create, which already returns validated. And I can use zip here. And here I'm simply creating a pair of a name and a phone number if they're both valid. Let's see how we can use this approach to validate our form. Sign-up data has a create email function that takes the name and the email. Here I'm validating the name with a function that returns null in case it fails. Then using from nullable to convert that to a validated. Map left is executed only if the thing is invalid. And I'm using it here to convert it from a string error to a form field error. For the email, again, we have a nullable type. So we use validated from nullable. We provide an error message in the lambda, and then map that error message to a form field error that has the email tag. And then both validations together, we use zip. We zip the validated name with the validated email and pass that to the sign-up data constructor. If we call it with the valid data, we get the valid result. Now we are done with the validation problem. Let's go back to the fail fast problem, which is we need to first validate the form and then call the API and abort on the first error. If we return nullable types from validated form, it's not going to work. We already saw that because there might be more than one error and different errors. We need to support different errors. Also, from the user repository, we cannot return a nullable token to signal the error because there might be different errors, like network might be down or the data might be invalid. So nullable types won't work here with our current requirements. But if we use nullable types, the compiler will make sure that errors are handled. To get better error messages, we can use a sealed class instead as the result. And here I have the sign-up result class that can be a success with the token, HTTP error with some error message, or a network error. So I can implement my sign-up repository to do a try-catch and use the retrofit sign-up function. In case of success, we get the token. In case of an HTTP exception, we need to convert that to a sealed result subclass. In case of IO exception, we get the network error object. For validating the form, we can also use a sealed class that has success with the sign-up data or an error with a list of errors. And we already saw how we can implement the validate form function that returns this. Then in our view model, we need to validate our form, and then we need to check the result. So here we need to check that body is form result.success. Then we call our repository function, and again we need to do a check to make sure it's a success. And the problem here is if we add more steps that can fail, we end up in the pyramid of doom that we have our code indented to the right, the more steps we add. Because for each step, first we need to check that the previous step worked, and only then we can do the next step. So if we use sealed classes for calling dependent functions that can fail, we get the support for better error messages, but it doesn't scale well with the number of steps. We risk the pyramid of doom, which looks like this. But luckily, there is a pattern here. The pattern is we call one function, we check if it worked. If the function worked, we call the next one. And that repeats. So Arrow offers some syntax sugar to help us with that. For failing fast and dependent computations, Arrow offers the either type that can be left with the type A or right with the type B. Again, it's a sealed class. And similarly to validated, we have extension functions to create these values, or we can also use the constructors normally. Now, if we have two functions that we want to call sequentially, where the input of the second function, where the input of the second function is the output of the first one. So here, validate form returns sign-up data in case it succeeds, and that's the input for submit form. We can use either and call them sequentially. Because they're sealed class, we can do the normal thing that we're used to and check if it's right and then do the next one. But this is arguably worse than using our custom sealed class. So let's see how either fixes this. Arrow offers the either computational block. And here, inside, we can call functions that return either, and we have access to this bind function. What this bind function actually does under the hood is it will check if the either is right, and only then it will call the next function. And that's the reason behind, even though validate form here returns an either of list of form errors or sign-up data, the type of form data here is sign-up data. We have access to the value in the case it worked, in the case it's right. And submit form is only called if validate form returns the right. And again, also for submit form, we have access to the token, and we can return it. Note that the result of the whole thing is still an either. In this case, either.right. with the value of the token. And if we call this with some invalid data, if the first function fails, then we get a left value with the errors, and submit data is never executed. So we can apply this now to our problem. There are errors that come from the backend. So for those, we need some data types so we can parse the error response. Here we have a form field DTO that has the field name and the list of errors. And then the sign-up error is the error message and the list of field errors, where the message is some generic error, and the list of errors are specific errors for certain fields. Arrow offers a retrofit adapter that supports parsing HTTP errors into the left side here. So if this fails with a HTTP error, like a 400, it will parse it into sign-up error DTO. We can modify the user repository to return an either of sign-up error or a token, where sign-up error can be a validation error, HTTP error, or an IO error. We can implement the sign-up function from our repository to use the either computational block. We take our data, input data, convert it to a body, And then we can use try catch and call our signup function backed by retrofit. In case it errors, we use map left to convert that to our domain error. We use the try catch for the IO error type, and we use bind here so we can get an access to the token, and we return the token if everything worked. In our view model, our validate form function will look like this. Based on the ID type, we either call create email or create a phone number that returns validated. In case there is an error, we can use map left to create a view state that includes those errors. And then we convert this to either so that we can chain it later with the repository call. And this works as you would expect. If the data is valid, we get the right value. If the data is invalid, we get the left value. And now we have a sign-up user function that takes a name and ID. It updates the UI to show the progress. We validate the form. We use bind. That means we have access to the sign-up data that we can use to pass it to the repository. Here, again, we use map left to convert that domain error to our updated view state that will include the errors. And then we return unit, because we're not updating the UI in case of success, but we want to do a navigation here. In the view model, when the user clicks the submit button, we launch a coroutine. We call our sign-up user function, and we use .fault. The first lambda is executed in case this fails. So we update the UI. The second lambda we can use to navigate home to the home screen. So to sum up, strategies for error handling in Kotlin are we can use exceptions for logic errors. We can use nullable types when we have a single failure and in the small on a function level. We can use seal types for multiple different failures and across architecture boundaries where we can carry that additional information. Arrow complements this with the validated type, which we can use for independent validations and accumulating errors, where we use the zip function to avoid the boilerplate of merging errors. We can use either when we have multiple different failures, where we have functions that the output of the first one is the input of the second one, and across network boundaries. Thank you for your attention. I will make sure you follow me on Twitter. Make sure you follow me on Twitter. The slides will be there. And I also have a sample project that demonstrates this. Thank you.